Today we're discussing reinforcement learning with human feedback, learning dynamic choices via pessimism. This paper addresses a key challenge in RLHF, learning optimal policies when direct reward signals are unavailable. Traditional RL relies on explicit rewards, but in real-world applications like training AI assistants, autonomous systems, or recommendation models, we often have only human choices, which can be noisy, biased, and incomplete. The problem is, how do we extract reliable learning signals from this? The paper introduces the Dynamic Discrete Choice (DDC) model, an economic framework that models human decision-making under uncertainty and bounded rationality. Instead of assuming humans always pick the best option, it recognizes that decisions are influenced by a mix of rational expectations and randomness. Using this foundation, the authors propose Dynamic Choice Pessimistic Policy, Optimization, DCPPO, to extract an optimal policy from human feedback. DCPPO works in three key steps. First, it estimates human decision policies and state action values, using maximum likelihood estimation, MLE, fitting past choices to a probabilistic model. Second, it reconstructs the hidden reward function by minimizing the Kreitken-Bellman mean-squared error, which helps approximate what humans implicitly value. Third, it runs pessimistic value iteration, a method that finds a near-optimal policy while accounting for uncertainty in human feedback. Why is pessimism useful? When learning from human data, we face off-policy distribution shift. The collected data only covers a subset of possible actions, meaning blindly following it can lead to errors. Pessimism ensures that the model doesn't over-trust unreliable data, instead favoring safer decisions supported by stronger evidence. This principle is widely used in offline RL to avoid overfitting to limited datasets. So, what does this paper solve? Previous RLHF methods lacked theoretical guarantees and struggled to generalize beyond observed human choices. DCPPO provides the first formal guarantee that learning an optimal policy is possible even when rewards are unobservable. The results show that its performance closely matches that of classical offline RL algorithms, proving that this approach is mathematically sound. However, challenges remain. The method depends heavily on the assumption that the DDC model accurately represents human decision-making. If real-world behavior deviates from this model, the learned policy may not be optimal. Another issue is that pessimism, while preventing overconfidence in unreliable data, can also be too conservative, avoiding potentially good actions just because they weren't frequent in the dataset. Finally, while DCPPO is designed for large state spaces, scaling efficiently remains a challenge. In summary, this paper advances RLHF by providing a structured way to learn policies from human feedback while ensuring robustness through pessimism. The DCPPO algorithm lays a theoretical foundation for learning in cases where human rewards are indirect and sparse. While there's room for improvement, this approach moves RLHF closer to practical applications where explicitly defining a reward function is difficult or impossible.